Hey boys, trying the old screen recording here to see how this works. Yeah, we'll see how we go. These are the notes that are on Canvas, or I will have put on Canvas by the time I upload this video. But this is kind of just me going through them as I would maybe in the classroom, something like that. So we're looking at polarization today, which is kind of as I've written here, more evidence for the wave theory of light. So remember, going back historically, it was Newton, his particle theory, the corpuscular theory, and versus Huygens, he had the wave theory. Everyone's like, oh yeah, Newton's the guy because he was much more respected. So they thought particles. Then Huygens did some work. Young did his double slit experiment to kind of show actually light is pretty much a wave. And then this was another kind of bit of evidence for light as a wave, polarization. So this is something that you can only do with if it was a wave. This is the guy that we're looking at today, and his name is the Frenchest name ever, Etienne Louis Malus. And he is the guy that has come up with Malus's law, which was published in 1809. So if you remember, Young's experiment was 1801, then this is 1809. So kind of the 1800s was like, yep, light is a wave. So here we get evidence that it's a wave. It's not, you would not be able to polarize a particle based thing, so it must be a wave. How does it work? Well, what do we mean by polarization? So here is a picture that we're hopefully all familiar with now, an electromagnetic wave. This is an example of light or microwave radiation or radio waves or anything like that. They have these oscillating electric and magnetic fields. So the red here is the electric field. So red is kind of going up and down like that. And remember, they're 90 degrees to each other. So red, electric field, up and down. And the magnetic field, the blue, is kind of in and out of the page. And we've kind of tried to draw that before. But that is the electromagnetic wave. And that is how, remember, they're kind of self-propagating, because you have a change in electric field here induces a change in the magnetic field, which induces a change in the electric field, and so on and so forth. So to polarize light, or to polarize any electromagnetic wave, it's kind of a way of filtering, filtering light. And very importantly, even though this is like the full kind of diagram of an electromagnetic wave with the electric and the magnetic fields, when we're going to look at pictures of polarization occurring, they only show the electric field. And that's because the polarizing filters act on the electric field by blocking or filtering the electric field. They don't really have any effect on the magnetic field. And obviously, if you're trying to draw an electric field and a magnetic field, can get a bit messy. So in these diagrams, they just draw the electric field and show it being polarized. But we just got to understand that with that electric field, there's an associated magnetic field. Okay, but we're just seeing the in the diagrams that are about to come up, we're just seeing the electric field. Okay, so this is Malus's law, and a key point that I'll make to begin with, that this applies to polarized light. So light that has already been polarized light, already been polarized by passing through one polarizing filter, and then it passes through another polarizing filter, and that's when it obeys Malus's law. So this I here is the intensity of the light coming out of the second filter. This I or I original, or I naught, is the intensity of the light entering that second filter. So it's the intensity of the light that's come out of the first filter. And then theta here is the angle between the plane of the electric field and the plane of the polarizing filter. So we'll look at what that means in a second. And I've written a bit later on, but it's also the same angle as the angle between the two filters. And I is equal to I naught cos squared theta. Remember, cos squared theta is different to cos theta squared. At this stage, maybe it might be a good idea to go and watch these two videos. I won't give you 7 minutes of me sitting here doing nothing, but you can pause the video and go and watch those videos. Classic Doc Schuster explaining it is very good. And then this guy here expands a bit more on some things that maybe Doc Schuster doesn't quite in his one. But both together give a pretty good idea of polarization. I think polarization is not too difficult to understand as well. So if we've watched those videos, let's just quickly have a look at what happens with polarization. So we've got unpolarized light. Okay, so an example of this could be like light from the sun or light from a light bulb. And this is where and again, it's only showing the electric field here. Okay, because imagine how messy this would be if we tried to draw the electric field orientated in all different directions and then as well the associated magnetic field. It would just be a mess. So we're just showing the electric field here, and you can see there's no kind of organization as to how the electric field is aligned. It's kind of in all directions. So there's a vertically aligned electric field here, and then like some angle here, some other angle here, all different angles. Then this is the polarizing filter. So the polarizing filter blocks certain angles of this unpolarized light of the electric field, and it lets some through. So you can, I guess it's pretty easy to see. This is a vertically orientated one, so only the vertical transmitted, only the vertically polarized. No, sorry, only the vertical unpolarized light can get through. Then it's the polarized light and it's through, and only the verticals made it through there. And this is called linear polarized light, or also plane polarized light. And this is polarized in the vertical plane. So that's the filter there. These ones at either end just kind of showing the oscillation of the electric field. Here it's unpolarized, so it's oscillating in all different directions. Here it's polarized, it's just oscillating up and down. So this Malice's law is not applying yet because we don't have polarized. This is not polarized light passing through a filter. This is unpolarized light. For Malice's law, you need to have polarized light entering that has come through a filter. So probably this light here entering a second filter, which we'll look at in a second. So for situations like this one, the unpolarized light compared to the polarized light, always the polarized light, if you put unpolarized light through one polarized filter, the stuff that comes out is exactly half the intensity of the original unpolarized light. So for example here, if I've got an unpolarized intensity of 15 CD, that's a unit, and there's a question at the end of this that gets you to work out or to look up what that is. So I won't say what it is, but 15 CD coming in, then the polarized intensity of it is going to be half that, 7.5 CD. So, but now we've got this polarized light. Okay, now we can put that through a second filter, and this is Malice's law. So here we've got the unpolarized light going through the first polarizer. We've got polarized light. Then we've got this same polarized light going through the second polarizing filter, polarizer 2 here, and being transmitted. So you can see here that the first polarizer has a vertically oriented plane of polarization, and so does the second polarizer. So only the vertical electric field is allowed through from the first one, and then because that can nicely sort of fit through that slot, well, then it's all going to go through the second one, and this area has the same intensity of this one. And that is because, so this is the middle diagram here. So if we go down here, the middle diagram, the angle between the incoming polarized light and the filter is 0 degrees. Here's the incoming polarized light, which is angled vertically. The filter is vertical. There's 0 degrees between them. Therefore, shut up Siri. Therefore, theta equals 0, cos theta equals 1. So in that equation back up above, all the way back up here, so cos theta equals 1, so cos squared theta, which is cos theta all squared, is going to be 1 as well. The intensity coming out of the second filter is the intensity going in to the second filter times 1. So it's just 100% of the light coming through. That's for that middle diagram there. And if we take this filter, second filter, and we rotate it, we turn it, we can eliminate the light, or some of the light coming through, depending on the angle that we turn this thing, some of the light coming through at the end. And the maximum effect of that is if we put it at 90 degrees. So here the first polarizing filter is vertically orientated, this is horizontally orientated, so 90 degrees. Then we've got theta equals 90, cos theta equals 0, therefore cos squared theta equals 0, therefore the light coming out is 0. And just say here, kind of, I guess for ease of understanding, that angle theta is as well as the angle between the incoming light and the second polarizing filter. It's the angle between the two polarizing filters, the planes of polarization. This has a vertical plane of polarization. This has a horizontal plane of polarization. So the angle is 90 degrees. That's the angle you can chuck into that formula. Before I go there, so I'll just show you a little simulation of this. And this is on the second document that I'm going to upload, the virtual prac. This is on there as well for you to have a play with. But basically, just can see this a vision of this kind of moving rather than still pictures. Here's the unpolarized light just showing the electric field again. Notice it's all in different directions, going through a first polarizing filter, which is vertically orientated, so only the vertical electric field comes through. And then all these subsequent filters are also at the moment vertically orientated, so we're just letting all the light through there, but we can change the angle of some of these. So if I put this to 45 degrees, let's say, okay, now you can see there's less of that light coming through. And if I, why don't I just have one here? If I adjust, so the more I turn that, the less I'm getting out of the bottom, or at the end of the thing. And then if I make it to 90 degrees, it's 89, so we're just getting a tiny amount of light through, and then 90 degrees, nothing. So if they're completely perpendicular to each other, the light coming out at the end is nothing. There's no light. Where do we see this kind of most commonly is in sunglasses. I always buy polarized sunglasses. They are the best. Especially when you kind of look at things like water things or the sky, makes it look so much cooler. Highly recommend. And the reason that is because certain surfaces, and water is a good example of this. When unpolarized light hits them, depending on the angle, this is just a bit further. Don't need to know this for the syllabus, but depending on the angle, that unpolarized light gets polarized by the water, the reflected light. So this could be light from the sun. This is the ocean, light from the sun coming in. We know some will go down and be refracted into the water, but some gets reflected, and that reflected light can be or is polarized with a parallel electric field. So the plane of polarization is parallel to the surface of the water. So, and this is if I'm standing here looking at the ocean, that's when if you don't have sunglasses on, that's when you see that kind of, the reflection of the light on the ocean. If you then put a pair of polarizing sunglasses on, what the polarizing filter in the lenses of those sunglasses is vertically orientated. So this is horizontally polarized light coming into a vertical orientated filter, it will get completely blocked off, so you don't see any of that reflected light. You still have the light coming, from the sun directly through your sunglasses and bouncing off other things, but the reflection off the water is completely eliminated. And so what it lets you do, it's really good if if you work on a boat, or like you're on a boat, or a fishermen use them as well, and things like that. But anyone can wear them, but it just kind of lets you see through the surface of the water, and you can see kind of into the what's underneath. And lots of any pictures that you see of like tropical locations that kind of taken for magazines or whatever, they're always taken through a polarizing filter, so you can see the difference here. Like if I'm trying to see the coral or something underneath the water here, then with a non-polarized, I get kind of reflections off the sun reflecting off the water. Here those reflections are cut down, and I can actually see what's underneath the water, and it just makes it easier to kind of see underneath. And this is also just a little bit of fun here for me, but the way that I shop for new sunglasses is to take my old sunglasses and hold them up like that to the display case, and any of the sunglasses that are polarized, because sometimes they say they're polarized, they say if they're polarized, and sometimes they don't say if they're polarized. But you can always check in this method, or if you don't have a pair of polarized sunglasses, just grab a pair that says they're polarized and hold them up to all the other pairs. And if the other pairs are polarized, the lens will go black like that, and you can tell, well, then both of those glasses are polarized. All right, so there's some questions there for you to answer, and you can submit this as the response to the assignment. Thank you.